Right now, top engineers at companies like, Tesla and Waymo are totally struggling to teach multi-million-dollar self-driving cars how to safely and reliably stop at a crosswalk.
Great. Yeah, it's a massive challenge.
Like, they are dealing with thousands of edge cases, sensor noise, and just environmental unpredictability. But across the country, an 8-year-old in a primary school classroom is basically solving that exact same fundamental logic problem.
They really are.
They are doing it using a handful of plastic bricks, a motor the size of a golf ball, and a visual interface that looks like a video game.
It is, it's just a remarkable parallel when you think about it. We tend to view industrial automation and artificial intelligence as these, like, impenetrable disciplines.
I was sure, like magic.
Exactly. Domains reserved strictly for postgraduate computer scientists working in, sterile laboratories.
Right.
But the fundamental logic architecture governing a multi-ton autonomous vehicle on a highway is, well, it's virtually identical to the logic architecture governing a plastic rover navigating across a third grader's desk.
Wow.
The scale and the stakes change, obviously, but the core engineering principles do not.
Welcome to the Deep Dive. I am incredibly excited you are joining us today because our mission is to unpack the building blocks of our automated future. And we are doing it by examining a platform you might normally associate with, stepping on barefooted in the middle of the night.
The absolute worst kind of pain.
Right, the worst. But we are looking at the Lego Spike ecosystem.
Yeah.
We have pulled from technical product overviews and introductory text on robotics and STEM, and some highly practical, on-the-ground insights from an educator's YouTube review, specifically Mr. Hino's Lego Robotics channel.
It's a great channel.
It really is. Okay, let's unpack this. We are looking at this not as a toy, but as a highly sophisticated hardware and software bridge. But I have to ask immediately, is this real engineering? Or is this just a massive toy corporation slapping the word STEM on a box to sell more plastic to school districts?
It's a totally valid skepticism. I mean, the term STEM science, technology, engineering, and mathematics has absolutely been commodified.
Yeah, it's everywhere now.
Right. But when you look at the pedagogical design of the Spike ecosystem, particularly how it handles the translation of abstract code into physical kinetic energy, you realize it is an incredibly rigorous educational tool.
Okay, so it's not just hype.
No, not at all.
Yeah.
This isn't about teaching kids to follow a manual to build a static spaceship. It is about demystifying the black box of modern technology. When a student successfully builds and programs a Spike robot, they are actively constructing a localized intelligence.
A localized intelligence. I like that phrase.
Yeah, they're learning how to map a digital rule set onto a physical environment.
So let's define the parameters of that localized intelligence, because our source text offers a foundational definition of robotics.
Right, we should start there.
It states that robotics is a branch of technology and engineering dedicated to making robots, which it defines as a machine that can perform a series of actions automatically.
Yes.
But that definition feels a bit broad to me. How? Well, if I set my automatic coffee maker to grind beans, heat water, and brew a pot at 6 a.m. every morning, it is performing a series of actions automatically. I wouldn't call my coffee maker a robot, though.
And you shouldn't. Mechanization is not robotics.
Okay, so what's the difference?
Your coffee maker operates as a static state machine driven by a rigid timer. It is completely blind to its environment. If you forget to place the glass crash under the filter, what happens at 6 a.m.?
It floods my kitchen counter with boiling water and coffee grounds, which I've definitely done.
Precisely. It executes its programming regardless of the physical reality around it. What the text is pointing to when it emphasizes STEM integration, and what these Lego kits are explicitly designed to teach, is dynamic reaction.
Dynamic reaction.
Okay, a true robot requires a feedback loop. It must be capable of ingesting variable data from its environment, routing that data through a localized processing unit, consulting a coded rule set, and dynamically altering its physical behavior based on that specific input.
Oh, wow. So it's constantly checking in with the real world.
Exactly. If your coffee maker were a true robot, it would have an infrared or ultrasonic sensor verifying the presence of the carafe before opening the water valve.
So it's the difference between a machine that just talks and a machine that actually listens to the room before it speaks.
That is a perfect analogy. And this brings us to why this specific type of education is an absolute mandate in the modern world.
Right.
We are no longer living in a purely mechanical age. We are living in a responsive, automated age. The sources emphasize that robotics teaches abstract skills like logical deduction, algorithmic thinking, and complex problem solving.
Which are crucial skills.
They are, but trying to teach algorithmic logic to a child using a whiteboard is, well, it's an exercise in futility.
Because it's invisible.
Yeah.
If you stand in front of a class of second graders and start lecturing about conditional loops and Boolean logic, they're going to mentally check out in 30 seconds.
Oh, absolutely. The human brain, especially in early development, craves tangibility. What's fascinating here is how robotics acts as a pedagogical Trojan horse.
A Trojan horse. How so?
Well, you give a child a goal, right? You say, build a vehicle that drives forward but stops before it falls off the edge of the table.
Okay, yeah.
To solve that, they have to utilize applied mathematics, physics, and coding. They have to hypothesize, test, fail, iterate, and retest.
Right, but they don't see it that way.
Exactly. They don't perceive it as a grueling math exam. They perceive it as a puzzle. The learning is entirely implicit.
They are too busy trying to save their plastic creation from plunging to its doom to realize they are mastering engineering principles.
Exactly.
So how does a platform actually facilitate this without overwhelming the user? Because, building a dynamic reactive machine is inherently complicated. If you put a pile of microprocessors and wires in front of a 7-year-old, you aren't going to get a robot.
No, you're going to get tears.
Right, tears and frustration. This leads us right into the philosophy behind the hardware itself, specifically looking at the differentiation between the two kits mentioned in our sources, Lego Spike Essential and Lego Spike Prime.
Yeah, the distinction between those two kits is a masterclass in managing cognitive load.
Cognitive load.
Yes, the educational philosophy here recognizes that the brain has a limited capacity for processing new information simultaneously.
Right, and Mr. Hino's review gives us a fantastic breakdown of the Spike Essential Kit, which is the foundational tool aimed at ages 6 and up.
It is.
He notes something that seems trivial at first glance. The kit comes with exactly 449 pieces, and the physical box utilizes color-coordinated sorting trays with matching stickers.
Right, the organization system.
Yeah, and he actually praised this setup specifically, noting how his students used to just dump all the pieces from the more advanced kits into a chaotic pile, which drove him crazy.
It sounds like a teacher just wanting a clean classroom, but if we connect this to the bigger picture, organizing those 449 pieces by color and category is actually the student's very first engineering lesson.
Wait, sorting plastic bricks into a white tray is engineering? I thought it was just glorified cleanup time.
No, think about any high-level technical environment. A surgical theater, an aviation maintenance hangar, a semiconductor clean room. What is the foundational operating principle?
That everything has a specific place.
Yes. The Japanese manufacturing sector calls it the 5S methodology sort. Set in order, shine, standardize, and sustain.
Oh, wow. I've heard of that in business.
Right. You cannot build or troubleshoot a complex, dynamic system if your component inventory is in a state of chaos. If an engineer is spending 20 minutes looking for a specific gear ratio, the cognitive momentum of the project stalls.
That makes total sense. You lose the flow.
Exactly. By forcing a 6-year-old to match the green structural beams to the tray with the green sticker, LEGO is bypassing the building phase entirely and instilling a systems thinking mindset.
Wow.
They are learning inventory management and structural organization before they even power on the localized hub.
That completely reframes the entire unboxing experience. You are establishing a professional laboratory environment disguised as primary colors.
Yes, exactly.
But this brings up a massive question regarding how schools or parents purchase these kits. Mr. Hino teaches kindergarten through 5th grade STEM. He uses this 449-piece essential kit across all those grades, scaling the difficulty of the lessons.
He does.
But if he has older kids or, highly gifted students, why wouldn't a school district just save the budget, buy the advanced Spike Prime kit, and just hand out fewer pieces to the kindergartners? Why silo them into an essential box?
Because of the paralysis of choice.
What do you mean?
Mr. Hino actually tested this. He explicitly states in his review that he tried using the Spike Prime kit with his second graders.
And it backfired.
Completely. He found they were entirely overwhelmed. The Spike Prime kit doesn't just have more structural pieces. It has a significantly more complex array of inputs.
Okay, like what?
Well, it includes a built-in gyro, advanced color sensors, and a tactile force sensor. When you place a highly sophisticated, variable-heavy kit in front of an 8-year-old, the sheer volume of interactive possibilities creates cognitive overload.
So they just freeze.
Yes, they spend all their mental energy just trying to figure out what the sensors are, rather than learning the foundational logic of how to connect a simple input to a simple output.
It's like trying to teach someone to drive using an 18-wheeler instead of a golf cart. The interface is too complex for the foundational lesson.
Precisely. Mr. Haino phrased it beautifully. He said the Spike Essential Kit is basic enough that students can branch out farther rather than reeling in from the Spike Prime.
Oh, I like that. Branching out.
If you start with a restricted, highly curated set of variables, a simple motor, a simple light matrix, the student quickly achieves mastery.
And mastery builds confidence.
Yes, mastery breeds confidence. Once they feel they have mastered the closed system, they naturally want to push its boundaries. They start asking, how can I make this motor turn faster? Or how can I make this light flash when it hits a wall?
They start innovating within constraints, rather than drowning in an ocean of options.
Exactly.
To give our listeners a concrete visualization, one of the projects mentioned for this essential kit is building a river ferry.
That's a classic introductory project.
Right, so you have an elementary student tasked with engineering a structure that has to physically traverse a space, carry a hypothetical load, and navigate a literal desktop river.
Yes.
They have to calculate the friction of the desk, the torque of the motors required to move the mass of the plastic ferry, and they have to write a logic script that tells the ferry when to start and when to stop.
And solving that river ferry challenge requires an understanding of the mechanical anatomy available to them. They need to know how to combine raw structural elements with electronic capability.
Let's dive into that anatomy. The introductory text uses a brilliant biomimicry analogy to explain the hardware.
I love this analogy.
It's so good. It suggests that a Spike robot functions essentially like a human body. You have the brain, you have the muscles, and you have the senses. This moves us from looking at a pile of parts to looking at an integrated biological system.
It is an incredibly effective framing device because it strips away the intimidating technical jargon. We intuitively understand human anatomy.
Right, everyone knows what a muscle does.
Exactly. We know that a brain processes, a muscle acts, and an eye perceives. Mapping those biological functions onto silicon and plastic makes the engineering immediately accessible.
So let's start at the top of the nervous system, the brain. In the Spike ecosystem, this is called the hub.
The hub, yes.
The text describes it as a yellow and white brick that houses the battery and acts as the central command center. This is where the code lives.
Right.
Now, to get the code from the student's laptop into this hub, the Prime kit relies heavily on Bluetooth. But Mr. Hino specifically points out that the Essential Kit utilizes a physical USB cable.
Which, from a deployment perspective in an elementary classroom, is a critical feature.
Really? I would assume wireless is always better. Cables seem like a step backward to me.
Well, in a sterile environment with one user, wireless is definitely superior.
Right.
But think about it. In a room with 25 kindergartners, 25 active Chromebooks, and 25 Bluetooth hubs broadcasting simultaneously, wireless is a network management nightmare.
Oh, wow. I didn't even think about that.
The interference and pairing issues alone would consume half the class time. The physical USB cable provides an immediate, foolproof, tactile data bridge.
It just works.
It just works.
Yeah.
It ensures the student's cognitive energy is spent on writing the code, not troubleshooting a localized network handshake protocol.
That makes a lot of sense. Eliminate the friction of setup. Now, this brain doesn't just receive code. It can also output visual data.
Yes.
The Prime Hub features an LED screen, while the Essential Kit uses a 3x3 light matrix. But here's where it gets really interesting. The Hub has a hidden sense.
Nice.
The text mentions a built-in sensor that knows if the robot is turning or tilting. Mr. Hino refers to this as the built-in gyro sensor.
The inclusion of a gyroscopic sensor inside the central hub is a massive leap in hardware capability. It grants the robot proprioception.
Proprioception, I know that term from biology. It's how a human knows where their limbs are in space even with their eyes closed.
Exactly. We rely on the vestibular system, specifically the fluid in our inner ears, to detect acceleration, tilt, and spatial orientation.
Right.
If you close your eyes and someone tilts your chair backward, you instantly know you are tilting, and your brain attempts to fire muscles to correct your balance.
Yeah, you get that falling feeling in your stomach.
Right. Well, a robot without a gyrosensor has no inner ear. It is functionally dizzy. It has no internal metric to understand its own physical state relative to gravity.
So how does a plastic yellow brick actually measure gravity and tilt? It doesn't have fluid in it.
No, it uses MEMS technology, micro-electromechanical systems.
Okay, what does that mean?
Inside that hub, there is a microscopic silicon chip. Carved into that chip are tiny tuning fork-like structures that constantly vibrate when power is applied.
Wait, really? Inside the brick?
Yes, microscopic moving parts. When the robot turns or tilts, the physical force of that movement, specifically the Coriolis effect, causes those microscopic structures to shift slightly.
That's insane.
It is. And this shift changes the electrical capacitance within the chip, which the hub then translates into a numerical degree of rotation.
That is just mind-blowing. We have microscopic vibrating tuning forks inside a Lego brick calculating the Coriolis effect so a plastic river ferry knows if it's capsizing.
It is industrial-grade aerospace technology scaled down for a primary school desk. It allows the student to write code that says, if the hull tilts more than 15 degrees, stop all forward momentum.
Speaking of momentum, let's move down the anatomical chart to the muscles. In this ecosystem, the muscles are the motors.
Right, the actuators.
The text explains that when the brain sends a command, the motors turn the wheels or articulate the robotic arms. But again, we see a divergence in the hardware based on the target audience.
Yes, there's a big difference here.
The text highlights that the Prime kit features powerful motors. Mr. Hino, holding up the essential motors, notes that they are definitely smaller but still have a pretty good amount of power.
This maps perfectly to the physics requirements of the two cohorts. The Essential Kit is designed for younger students building lightweight, conceptually simple mechanisms.
Like the river ferry.
Exactly. A river ferry doesn't require massive torque, it requires basic propulsion.
Right.
But as a student ages into the Prime Kit, they are tasked with building industrial arms that have to lift physical payloads or rovers that have to traverse high-friction terrain.
So they need more torque.
They do, which requires a larger motor housing, more copper winding, and more power draw from the battery. The mechanical complexity of the muscle scales with the mathematical complexity of the curriculum.
Okay, so we have a brain with an inner ear, and we have muscles capable of kinetic output. But how does this system interact with anything outside of itself?
Right, it needs to see the world.
Yeah, if it only has proprioception, it only knows its internal state, it needs external senses, it needs the peripheral nervous system.
Without external sensors, a robot is just a pre-programmed puppet. Sensors allow it to perceive reality.
Our sources highlight three main sensors. First, the eyes. The text describes a distant sensor that measures how close an object is.
Yes, these rely primarily on ultrasonic technology.
Like ultrasound.
Similar concept. The sensor emits a high-frequency sound wave, imperceptible to human ears, that travels outward, strikes a physical object, and bounces back to a receiver on the sensor.
Like echolocation, like a bat.
Precisely. And because the speed of sound in air is a known constant, the hub can calculate the exact distance by measuring the time it took for the echo to return.
Wow. But I imagine that introduces some fascinating real-world variables, because sound doesn't bounce perfectly off everything, right?
Oh, definitely not.
What if the river ferry is approaching a dock made out of something soft, like a sponge or a piece of felt?
This is exactly where the engineering education shines. A soft surface will absorb the ultrasonic wave, meaning no echo returns, and the robot thinks the path is clear.
Oh no, so it just crashes right into the dock.
It does. Or, if the object is angled at 45 degrees, the sound wave deflects away rather than bouncing back to the receiver.
Suddenly, the student's perfect code fails in the physical world.
Yes. They have to troubleshoot not just the software, but the physical limitations of acoustic physics.
They learn that sensors are not magic. They are subject to environmental interference. That's a massive lesson.
It really is.
Okay, the second sense mentioned is the color sensor, which is included in both kits. The text says it can see different colors on the floor.
This utilizes an RGB LED to bounce light off a surface and a photodiode to measure the intensity of the reflected red, green, and blue light.
So a student could map a route using colored tape, like follow the black line, turn right at the red square.
Exactly. Line-following robots are a staple in these classes.
But again, environmental variables matter. If the classroom is flooded with bright sunlight, does that interfere with the sensor's ability to read the reflection?
It absolutely can. Ambient light contamination is a classic robotics problem. The students learn they have to calibrate their sensors based on the environmental conditions of the room.
The third sensor is where we circle back to Mr. Hino's warning about cognitive overload. The Prime kit includes a force sensor.
Yes, the tactile sensor.
The text describes it as feeling pressure, when the robot bumps into a wall.
But this isn't just a binary on-off bump switch. A true force sensor measures the mechanical resistance in newtons. It allows the robot to understand how hard it is pushing against something.
And that explains why the second graders were overwhelmed.
How do you mean?
Well, with a color sensor, the logic is simple. See, red, stop.
Mm-hmm.
But with a force sensor, the logic is nuanced. Drive forward until you encounter 3 newtons of resistance, which means you are gently touching the payload, then engage the lifting arm.
Right.
Asking a 7-year-old to conceptualize abstract units of physical resistance and map them to a coded variable is a bridge too far.
It is. It requires an understanding of applied physics that they simply haven't developed yet. But what's vital to recognize here is that when you assemble these components, the processing hub, the ultrasonic eyes, the RGB optical sensors, the gyroscopic inner ear, and the motorized muscles, you have constructed a complete, localized, artificial nervous system.
But a nervous system is just dormant meat and electricity without a mind.
Very true.
It needs consciousness, or at least algorithmic instructions.
Yeah.
How do we bridge the gap between human intent and machine execution? This brings us to the software side of the equation.
The hardware is the potential. The software is the realization of that potential.
The text states very clearly, building the robot is only half of the job. To make it smart, you need to write a program.
Yes.
Now, the Spike ecosystem offers 2 distinct pathways for this, which again highlights their pedagogical philosophy. Let's look at the first path word blocks, which is based on the Scratch programming language.
A fantastic tool.
The text notes that you don't write text. You snap together colorful puzzle blocks on the screen. For example, a yellow when play-clicked block snaps into a blue move forward block, which snaps into a green for 3 seconds block.
It is a purely graphical interface for logical architecture.
But I have to push back hard here. Is this real coding?
I get that question a lot.
Because when I think of programming, I think of a blank text editor writing raw syntax. If a child is just dragging and dropping colorful jigsaw puzzle pieces on an iPad, aren't we creating a false sense of security?
Right, that they aren't doing the real work.
Yeah. Aren't we just delaying the inevitable pain they're going to face when they graduate to a real language and suddenly a single missing comma breaks their entire multi-thousand-line program?
That is a very common critique from traditional computer scientists, but it fundamentally misunderstands the cognitive barrier to entry in computer science.
How?
Yes. Eventually, an engineer must learn the brutal, unforgiving reality of syntax. But if you introduce syntax at the exact same time you are introducing structural logic, you destroy the student's motivation.
Because they fail constantly before they ever see a result.
Precisely. Let's say a 10-year-old wants to write a simple conditional loop. If the distance sensor reads less than 10 centimeters, stop the motor. Otherwise, keep driving.
Okay.
Conceptually, the child understands that logic perfectly. It is a sound architectural thought. But if they have to type that in a language like C++ or even Python, they have to worry about indentation, colons, brackets, and case-sensitive variable calls.
Oh yeah, the syntax tax.
The syntax tax, exactly.
Yeah.
If they capitalize the S in sensor when the library defined it with a lowercase s, the compiler throws a fatal error.
The program crashes.
The program crashes. And the child receives immediate negative feedback. They are told they are wrong.
That's discouraging.
Extremely. But they weren't wrong about the logic. They were wrong about the grammar.
Ah, I see.
The brilliance of visual block coding like Scratch is that it completely eliminates that syntax tax. The shape of the blocks dictates the grammar.
Because they physically lock together.
Right. A rounded Boolean variable block physically cannot snap into a square integer input. Because the environment prevents grammatical errors, the student is free to focus 100% of their cognitive load on mastering control structures.
Like loops and conditionals.
Exactly.
Yeah.
Loops, conditionals, arrays, and variables. They learn how a computer thinks without being punished for not knowing how it spells.
Okay, that is a profound defense. You're separating the mastery of logic from the mastery of linguistics.
Yes.
You give them a sandbox where logic works perfectly every time, which builds their architectural confidence.
That's the goal.
But eventually the training wheels have to come off.
They do.
And the text points out that Spike Prime explicitly facilitates this transition. Once they master block logic, they can switch to Python.
Which is not a toy language.
Not at all.
Python is the dominant language for machine learning, data science, and advanced robotics worldwide.
It is a massive jump. But the text claims that learning Python through robotics makes text-based coding much easier and more visual. How does a physical robot make typing text on a screen easier to understand?
Because it creates an immediate physical, kinetic mapping of abstract, object-oriented concepts.
Kinetic mapping.
Let me explain. In a traditional high school Python class, a student types print, hello world, and text appears on a blacked terminal screen.
Right.
It is an abstract input resulting in an abstract digital output. It feels hollow.
Yeah, it's not very exciting.
But with Spike Prime, a student types a line of Python, for instance, instantiating a motor object and calling a method, motor a.run for degrees 360.
Okay, so they write that code.
When they execute that script, the Fresnel motor sitting on the desk violently whirs to life and rotates exactly one full circle.
It turns invisible code into kinetic energy.
Exactly. The abstract syntax instantly becomes physical reality. If they type 360, it spins once. If they change the integer to 720, it spins twice.
It's so cool.
They can literally see, hear, and feel the variables they're defining. It provides the ultimate, undeniable feedback loop for their programming.
So we have the hardware biomimicry, the sensors and motors. We have the software bridge from syntax-free scratch blocks to object-oriented Python.
Yes.
How do these two domains interact in real time when the robot is actually navigating the physical world?
That's the big question.
What is the core processing loop that governs this artificial intelligence? This leads us to our final and arguably most critical engineering concept, the IPO loop.
Input, process, output. It is the holy grail of systems engineering.
The text introduces this as the foundational concept behind every Spike Prime robot. Let's walk through it meticulously, because this is where the magic becomes math.
Let's do it.
Visualize our river ferry, or perhaps a simple four-wheeled rover driving across a desk. It has the hub, the motors, and the ultrasonic distance sensor on the front.
Okay, the robot is in motion.
Step 1 is input. The text says the sensors collect data from the environment.
Right.
The rover is driving, and suddenly you place a heavy textbook directly in its path. The ultrasonic sensor fires its sound wave, the echo returns, and it calculates that the obstacle is exactly 10 centimeters away. The hardware has generated raw data.
But data without context is useless. The sensor itself does not know what 10 centimeters means. It just passes the integer to the hub.
Which triggers step 2 process. The text states, the hub reads this data and decides what to do based on your code.
Yes.
The brain receives the integer 10. It then rapidly scans the Python script the student wrote, looking for a conditional statement related to distance.
Right. Let's say the student wrote, if distance is less than 15 centimeters, initiate stopping sequence.
The processor acts as the arbiter. It compares the raw environmental input, which is 10 centimeters, against the established digital rule set, which is less than 15 centimeters.
The condition is met. The logic gate opens. A decision is formulated.
And that decision dictates step 3 output. The text says, the robot takes action. The hub sends a high-level electrical command to the motors to cut power and apply physical braking force. The wheel stops spinning. The rover halts inches from the textbook.
Input, process, output. It is a continuous high-speed pulling loop. The hub is likely running that loop dozens of times per second, constantly checking the environment against the code.
It is incredibly elegant. But I have to ask, is this really how real-world automation works? I mean, this is a plastic toy on a desk. Is this genuinely preparing someone for an engineering career?
If we connect this to the bigger picture, the implications of this exact loop are staggering. Think back to the Tesla and Waymo engineers we mentioned at the very beginning of this deep dive.
The one struggling with crosswalks.
Yes. How does a self-driving car avoid hitting a pedestrian? It uses a multi-million-dollar LiDAR array and stereoscopic cameras. That is the input.
Yeah.
It feeds gigabytes of visual data per second into a liquid-cooled neural network supercomputer in the trunk. That is the process.
Yeah.
The computer actuates a massive hydraulic braking system to halt a 3-ton chassis. That is the output. The hardware is infinitely more complex, the data volume is astronomically higher, and the latency requirements are literally a matter of life and death.
But the architecture is exactly the same.
The architecture is identical. Gather data from the physical world, compare data to a coded logic state, execute kinetic action based on the result.
Wow.
The 10-year-old programming a Lego rover to avoid a textbook is practicing the exact same logical architecture as a senior autonomous systems engineer. They're speaking the exact same structural language.
So what does this all mean for you, the listener? The text's conclusion frames this perfectly. It says, learning Spike Prime is not just about playing with Lego bricks. It is about understanding the future.
I couldn't agree more.
By mastering this loop, a student is developing the mindset of a future engineer and creator.
They are undergoing a fundamental paradigm shift. Most of the population navigates the modern world as passive consumers of magic.
Consumers of magic.
Yeah, the automatic sliding doors at the grocery store open, and it's just convenience. The smartphone adjusts its screen brightness based on the room, and it's just a neat feature.
But someone who understands the IPO loop sees the matrix.
Precisely. They walk up to those grocery store doors, and they don't see magic. They see a passive infrared motion sensor generating an input, a localized logic board running a process, and a pneumatic motor executing an output.
They understand the causality of the automated world.
They move from being subjects of technology to being potential masters of it.
They see the code behind the curtain. And that empowers them to realize that the automated systems governing our lives aren't infallible black boxes created by untouchable geniuses. They are just complex iterations of the exact same logic loops they built on their desk with plastic bricks.
It's an empowering realization.
We have covered a massive amount of ground today. We started by exploring how physical hardware combats the abstract nature of coding.
We did.
We looked at the extreme pedagogical intentionality behind the Spike ecosystem. From the 5S inventory management of the Essential Kit's color-coded trays to the cognitive load management that prevents second graders from being paralyzed by advanced sensors.
And we dissected the biomimicry of the hardware.
Right.
The MEMS technology inside the gyroscopic inner ear, the ultrasonic calculations of the distance eyes, and the torque differentials in the motorized muscles.
We defended the software bridge, unpacking how Scratch eliminates the syntax tax to foster logical architecture.
Which then seamlessly translates into the real-world kinetic execution of Python text code.
And we grounded it all in the elegance of the IPO loop, the exact same system powering our autonomous future.
It is a remarkable synthesis of physical engineering and digital logic. But as we wrap up, this deep dive raises an incredibly important question, something I want to leave you to mull over long after this audio finishes.
Ooh, okay. What is it?
Today, we have discussed how we use code, sensors, and the IPO loop to teach these machines how to safely navigate our messy, unpredictable human environment. We teach the rover to stop for the textbook. We teach the car to stop for the pedestrian.
We force the machine to adapt to us.
Exactly. But as these automated systems, autonomous logistics networks, delivery drones, medical robots, self-driving fleets become more advanced and more deeply integrated into the infrastructure of our daily lives, we have to question the long-term trajectory of this relationship.
Where is the IPO loop taking us?
If the fundamental limitation of an automated system is the clarity of its input, how long will it be before our physical environments, our cities, our roadways, our hospitals, our homes, are entirely redesigned and coded to accommodate the sensory needs of the robots, rather than the comfort of humans?
Wait, really? You think we'd change our cities for them?
Think about it. Will we start replacing visual street signs with embedded RFID chips purely so autonomous vehicles have cleaner inputs?
Oh, wow.
Will our architecture prioritize the navigational logic of delivery drones over the aesthetic preferences of human residents? Ultimately, as we build these artificial nervous systems and deploy them into our world, we have to ask, who will really be adapting to whom?
Are we building a world for humans with robots in it? Or are we slowly building a world optimized for the machine's IPO loop?
That's the real question.
That is an incredible, slightly terrifying thought. You thought we were just talking about colorful plastic bricks today, didn't you? Thank you so much for joining us on this deep dive. Until next time, keep unpacking the logic of the world around you.